let's go ahead and see. Can I see my hand? Yes, I can. And can I hear myself? Yes, I can. All right, that takes care of our sound check. Let me go ahead and put away the headset. And let's see what we're gonna do today. Somehow I'm even less prepared this week than I was last week, but we will carry on. I was expecting the recording from last week's session to not get as much attention, but boy was I wrong. It ended up getting more attention than both of the previous stream recordings combined. So that's something. I would have thought, since fewer people get into a calculus-based electromagnetism course in the first place, that there'd be a smaller audience for it, but just goes to show how unpredictable people are. Let me see, what was I going to do for today? Continuing from last time. Not there. I remember we were doing a problem with a conductor. Right, and I was thinking of doing an insulator version of the same problem. So yeah, let's go ahead and do that. Let's just continue where we left off last time. And maybe this time we'll also add the concept of voltage to the mix while we're at it. Okay, so last time we had a spherical shell with a point charge inside it, and it was a conducting sphere. So this time I'm going to do pretty much the same thing. So we're going to have a charge of Q1 inside of a sphere, and then this sphere, this spherical shell, I should say, will be an insulator this time. So let me go ahead and extend it like that. Okay, I think that's a pretty decently drawn spherical shell. Basically have it sliced in half, and we're looking at the inside of it. So we've got a charge of Q1 in there, and then we've got a total charge of Q2 on the outer part of it. And let's say that this thing is uniformly charged. So this charge Q2 is uniformly distributed throughout the spherical shell. And let's do the same things we were doing last time. Let's find the electric field in all regions of interest. Here we go. So electric field as a function of R how many regions of interest do we have? And I forgot to mark. This is going to have an inner radius of A and an outer radius of B. Okay, how many regions of interest do we have to work with? Well, we've got from 0 to A, so we've got 0 less than R less than A. we've got between A and B, so we've got A less than R less than B, and we have everything outside of B, so we've got R greater than B. And like I said last time, you can place the or equal to here or here for the B and here or here for the A. It doesn't really make that big of a difference. I'm not going to split hairs over it, at least. If your professor is particular about it, then just follow what they say. But that will be it for defining our regions of interest. So let's see. A good Gaussian surface to go with, of course, when you're dealing with spherically symmetric situations, would be a sphere. No surprise there. Same thing we did before. So if I imagine a sphere of radius between 0 and A surrounding this charge Q1, centered at this charge Q1. Then, actually, let me see, did I draw over the image last time? Kind of. I'm not going to draw the innermost one just because I don't want to ruin this drawing too much. I want to save that for the middle, for the second region of interest, because that's the one that will be the most difficult for most students. So if we imagine a sphere wrapping around this point charge, we're not going to be too surprised when we use Gauss's law to find that the electric field within this area is simply the electric field of a point charge. So let's see, total flux equals the integral of E dot dA, and we justified last time because of symmetry that it just becomes the integral of E times dA, and if you integrate the dA, then you just get the area, in this case of our Gaussian sphere, equals charge enclosed over epsilon 0, or epsilon naught if you prefer. Okay, getting that charge enclosed is usually the hardest part with these problems. For this one, pretty easy because the only charge we have is the point charge Q1. So let's see, we have the electric field times the surface area of our sphere would be 4 pi r squared. And then charge enclosed is Q1 over epsilon naught. We can divide by 4 pi r squared on both sides, and that'll give us electric field equals Q1 over 4 pi epsilon naught times 1 over r squared. And yeah, that is it. So that one is pretty simple, straightforward. Q1 over 4 pi epsilon naught times 1 over r squared. Okay. And then we get to the next region of interest, where our Gaussian sphere has a radius between A and B. So something like this cuts through here. Like so. This is where it gets tricky. So, most of this is going to be the same. The only difference now is the charge enclosed. So we've got electric field times 4 pi r squared equals, the charge enclosed is two things. The charge enclosed is equal to Q1 plus a fraction of Q2. I'm going to call it Q shell. Yeah, I'm going to call it Q shell, which is not the same as Q2. And all that over epsilon naught. Okay, the Q1 is the easy part. The Q1 just, you can split this into two fractions. You can call it Q1 over epsilon naught plus Q shell over epsilon naught. And that will give us the opportunity to just take this part out of our mind for a second while we really try to focus on how much charge is inside the Gaussian sphere of radius between A and B. How much charge is actually in there, expressed in terms of Q2. So, in order to figure this out, we need to figure out how much volume of our shell is enclosed. So I'm going to say Q shell is equal to, let's see, it's going to equal, well, the volume density of the spherical shell times the volume of the shell that's actually enclosed. Should I call it V enclosed? No, I'm going to call it V shell. So it's going to be charge per, I guess, cubic meter times the number of cubic meters that we actually have wrapped in. Wrapped in? Am I using the right word? Hold on. That we have enclosed by our Gaussian sphere here. Okay, first off, let's figure out the total charge density, assuming that the charge Q2 is distributed uniformly throughout the spherical shell. All we would have to do is say that the charge density of the shell is equal to the total charge, Q2, divided by the total volume. Of the shell. And I guess I probably should have used different subscripts for my variables here, because I can see how this can get a bit confusing. So the total volume is everything from A all the way to B. What I want to do to get that total volume is simply realize that a spherical shell is just two spheres, a big sphere minus a little sphere. So if I do that, then I can say that this is equal to Q2 divided by, let's see, the volume of the outer shell of radius B is going to be, volume of a sphere is 4/3 pi r cubed. Volume of a sphere, this is just a formula you should know from geometry, is 4/3 pi r cubed. And so the volume of the outer sphere would be 4/3 pi b cubed minus the volume of the inner sphere would be 4/3 pi a cubed. So if I factor out the 4/3 and pi, 4/3 pi, then I'm left with b cubed minus a cubed. And there we go. That is the charge density within our spherical shell. Now, to get the volume of the shell, I'm going to call it volume of shell enclosed so that we can make it a little more distinct. Okay, what volume of our shell is actually enclosed? Well, in our region of interest, the radius of our Gaussian sphere is less than b. It's somewhere between a and b. So it's greater than a but less than b. So it's not going to include all the charge of the shell. It's only going to include a portion. And the volume portion that it includes would just be the volume of a sphere of radius r greater than a minus the volume of a sphere of radius a. So pretty much the same thing we did up here, except we don't go all the way to b cubed. We go to r cubed, which is some value less than b. So I guess I will write that. Where do I want to write that? I'll write that over here. V shell enclosed is equal to 4/3 pi r cubed minus 4/3 pi a cubed. So 4/3 pi can be factored out, and then we'd have r cubed minus a cubed, where r is whatever, let me use a different color for this, where r in this case is whatever that distance is. Something larger than a, but still smaller than b. Okay, so with these two pieces, I should now be able to calculate Q shell, or at least get an expression for it. So Q shell is equal to, let's see, we would have Q2 over this stuff times that stuff. So I can see that the 4/3 pi is going to cancel, which is nice. Very convenient for us. So I have Q2 over 4/3 pi b cubed minus a cubed, all times 4/3 pi, and then I don't think I have enough room for it, r cubed minus a cubed. Yeah, this was not the right place to start writing this. Oh my goodness, and that's not even readable anymore. But if I go ahead and cancel out the 4/3 and the pi, then I can rewrite it over here, hopefully a little bit more clearly this time, and we are left with Q2 times, that's r cubed minus a cubed, over b cubed minus a cubed. And we can see when r reaches the value of b, this just becomes b cubed minus a cubed over b cubed minus a cubed, which equals 1. So the total charge at that point, once your Gaussian sphere reaches a radius of b, would just be the total charge of the shell. So that makes sense. I don't see any indication that we've made any sort of mistakes here. So putting this together with this, oh boy, we're going to have quite the expression here. It's not going to be very pretty, but if we divide by 4 pi r squared, if we divide that 4 pi r squared over to here, then we're going to have Q1 over 4 pi epsilon naught times 1 over r squared plus Q shell over 4 pi epsilon naught r squared. Oh my goodness. I don't think I left enough room to even fit the expression in here. Nope, definitely not. Unless I really try to squeeze it all in here. Q2 times r cubed minus a cubed over b cubed minus a cubed. I don't even know if that's readable. I can sort of see it on the preview screen. I don't think it's that bad, especially since I'm reading it out loud. And then all that times 1 over r squared. Okay, there we go. The expression looks complicated, but if you slow down and really think about your geometry, then you can confirm that it is correct. And I guess you might want to simplify this a little bit because having a fraction within a fraction isn't very pretty, so you might want to, let's see, move the whole b cubed minus a cubed term down to the denominator to make it look a little bit prettier, but other than that, we're good to go with that one. And then for the third region of interest here, a Gaussian surface of radius greater than b, a Gaussian sphere of radius greater than b, it would just include all of the charge. So for that one, electric field times surface area of a sphere is 4 pi r squared equals the total charge enclosed. Now there's no question about it. It's all of Q1 plus all of Q2 over epsilon naught, and divide by 4 pi r squared, and we're done. So we get Q1 plus Q2 over 4 pi epsilon naught times 1 over r squared. Okay, that wasn't too terrible. I mean, I would have liked to come up with better names for my variables over here during the most difficult part of it, but otherwise it wasn't that bad. Alright, so that takes care of spherical symmetries. Let's have a look at, what does my book have? My book has a situation where you've got a line of charge and a charged cylindrical shell. And is this thing an insulator or a conductor? It says it's an insulating shell. Okay, we can work with that. Alright, so what they've drawn is, I'm going to draw the cylindrical shell first, and then I'm going to figure out how I want to draw the infinite line of charge. I probably should have drawn it a little bit thicker so that I'd have room to write in this space in between, but poor planning on my part. Okay, something like this. And then inside of it is an infinite line of charge. Supposed to go down the middle. I guess I didn't draw it very well. It's supposed to be parallel to those other two lines. Yeah, it's supposed to be right along the axis of the cylinder. Okay, so is there any information here that we want to use, or should I just go ahead and assign numbers myself. It says you've got an infinite line of charge with a linear density of lambda. We'll just, again, avoid the use of numbers like I did last week. Let's see, and then the cylindrical shell is uniformly charged with a volume density of rho. Okay, so we didn't assign a linear density to it, and that's the first thing they ask. What is the linear charge density? Okay, this is actually a pretty good question. Pretty good question to start us off. So this infinite line of charge has a linear charge density lambda 1, and the cylindrical shell, which has inner radius A and outer radius B, has a volume charge density rho. And they want us to find what is lambda 2. What is lambda 2 linear charge density of this cylindrical shell? Linear density of the cylindrical shell. And I don't know if I mentioned this yet, but both this line of charge and the cylinder are infinite in length. Okay, how do we find this lambda 2? Well, we can do pretty much what we just did earlier with finding the volume charge density of our insulating sphere, of our insulating spherical shell. What we did here was we took the total charge divided by the total volume. If we want a linear charge density, we take the total charge divided by the total length. So lambda 2 is equal to Q total of the cylinder over the length of the cylinder. Okay, what is our total charge? Well, our total charge can be expressed in terms of our volume charge density. We can say that the total charge on the cylinder is equal to the volume charge density of the cylinder times the volume of the cylinder. I should be saying cylindrical shell, but cylinder is shorter to write, and this is the only cylindrical object in this whole entire problem, so I don't think it's too vague to just use the term cylinder here. Okay, how do we express the volume of that cylindrical shell? Well, it's kind of what we just did with the spherical shell. A cylindrical shell can be thought of as two cylinders, a bigger cylinder minus a smaller cylinder that got hollowed out of it. So I can do equals rho times, let's see, volume of a cylinder. If you remember the formula for it, it's supposed to be base times height. The base of a cylinder is a circle, and area of a circle is pi r squared. So area of the base times height, pi r squared times, well, in this case the cylinder is standing sideways, but the height that we would use is the length of the cylinder. It's infinite, yes, but we're physicists, so we can get away with what we're about to do here. So, volume of the cylindrical shell, we're going to have pi times outer radius squared, so pi b squared, times L, minus pi a squared times L. Factor out the L. Pi b squared minus pi a squared times L cylinder. I'll just call it L sil for short. Okay, if we go ahead and take this expression and plug it back into here, then we now have rho times, actually I can also factor out the pi, rho times b squared minus a squared times pi times L cylinder over L cylinder, whatever the length of this thing is, it cancels out. We can get away with canceling these infinite lengths because we're not actually working with an infinite length. That's just something that we assume to simplify our calculations a little bit. If we did this in practice, we would be working with some sort of cylindrical cable that's very long, yes, but not infinitely long. So we can get away with canceling this length. Let me see, is there anything else I want to comment on here before I proceed any further? I don't think so. The only other thing I would do is I would move the pi closer to the front just to make it look nicer. And lambda 2 is equal to, I'll write it over here, lambda 2 is equal to the given volume charge density times, I forgot the pi. Let me try that again. Lambda 2 equals rho pi times b squared minus a squared. And that's on the cylindrical shell. Alright, that takes care of one item. Did they ask for anything else? Of course they asked for something else. It's an entire paragraph of a problem. Let's see, they're asking for electric fields in different regions. I was going to ask for that anyway, even if they didn't. Yeah, I think I can ignore all those other questions. Let's just go ahead and figure out the expression for the electric field in our different regions of interest. Alright, so first region of interest is going to be between here and here, so before you reach the inner surface of the shell. Second region of interest is within the shell, so between r equals a and r equals b. And then finally we'd have a third region of interest where your Gaussian surface surrounds the entire thing, both the line of charge and the charged shell. Okay, for our Gaussian surface we're going to use a cylinder for reasons that are probably obvious by this point. The symmetry of a cylinder is advantageous in situations like this. So let me see. I guess I'm going to write electric field equals, and then for my regions of interest, I'm going to have when the radius of my cylinder is between A and B, then, wait, not between A and B, what am I doing? Between 0 and A first, 0 and A, then between A and B. And finally, for a cylinder of radius greater than B. I'm going to have 3 different electric field expressions to consider. Okay. Let's see what we can do with all this. So first off, if I imagine a cylinder centered around this infinite line of charge, I give it an infinite length, just like my line, and any flux going through it would be, I guess I'll actually try and draw it this time. So if I draw a cylinder like that, whose radius is somewhere between 0 and A, and it just extends infinitely and wraps around the entire line of charge, any flux going through it is going to go through its side surface. It's not going to go through the base. The electric field lines from the infinite line of charge all point radially outward. Something like that. They point straight outward from the center. None of them are pointing in that direction, along either direction along the axis of our system. So I don't need to consider the flux through the 2 bases of my cylinder. Not that we'd ever even be able to reach the bases, because this is supposed to have like an infinite length, but even if it wasn't infinite in length, all of our electric fields, none of them are going to be popping out of or into the circular bases, so I don't need to consider those at all. That leaves me with just the side surface area, and the side surface area of a cylinder is what again? What is the side surface area of a cylinder? A side of a cylinder. It's going to be 2 pi r times the height, or in this case 2 pi r times L. And how do we know that? Well, if I take a piece of paper here and I roll it up into a cylinder, here, hold on, let me bring it a little bit lower, something like this. There we go. So this is going to be 2 pi r, and if I do 2 pi r times, this would be the length over here. So if I take the 2 pi r, if I unroll this thing, that's my 2 pi r multiplied by the length. 2 pi r times length. When you unroll your cylinder, what you get is a rectangle. And you know the area of a rectangle, it's just the width times the height. Well, this width used to be 2 pi r back when this thing was rolled into a cylinder, and this height is L. So there you go. The side surface area of a cylinder is 2 pi r L. And hopefully with that, you will never forget this formula. If you ever forget the formula for the side surface area of a cylinder, just take a piece of paper and roll it into a cylinder, and you'll see why the circumference of the base multiplied by the height of the cylinder gives you its side surface area. Anyway, where did I want to go with this? So we need that side surface area to get our electric field from Gauss's law. So let's go ahead and write down Gauss's law. The flux equals integral E dot dA equals charge enclosed over epsilon naught. And integral of E dot dA becomes the integral of E times dA, because the direction of the electric field is always going to be perpendicular to the Gaussian surface that we've chosen. So the dot product is just going to give us a cosine of 0, because dA is also defined to be in a direction that's perpendicular to the surface. So electric field perpendicular to the surface, dotted with an area differential that is also directed perpendicular to the surface. That's an angle of 0 between them. Cosine of 0 is 1. So it just reduces to simple multiplication. So that leaves us with E times the integral of dA. Oh, well, I guess, yeah. E times the integral of dA. The reason I can pull this E out is because, again, due to symmetry, I can assume that the electric field at this part of the surface is the same as the electric field at this part of the surface, and this one, and this one, and this one. So I can assume the same magnitude of electric field at all points of equal distance from my line of charge. So then that magnitude is constant and can be factored out. Integral of dA is just going to give us the side surface area of the cylinder, which is the 2 pi RL from earlier. And charge enclosed, I guess I'm going to have to find an expression for that over epsilon naught. Okay, what is our charge enclosed when we have a Gaussian cylinder wrapped around an infinite line of charge whose density is lambda 1? Well, in that case, it would just be Q line equals the density of the line times the length. Lambda 1 times L. I guess I should call it L cylinder, but it's the same L that we've been using for this whole entire problem. It hasn't changed. So it's going to be lambda 1 times L. Charge per length times length gives us the total charge enclosed from our infinite line of charge. And let me actually do this so that we don't get those two equations mixed up with each other. Okay. For the left-hand side, I want to write the integral of dA, which is just going to be the area. I'm going to replace it with 2 pi RL. So that leaves me with E times 2 pi RL. Is that visible on screen? Yes, it is. Equals lambda 1 times L over epsilon naught. Is that still visible on screen? No, it isn't. Well, it's barely even visible on the paper. The L's cancel out, which is nice. And if you divide by 2 pi r, then we get electric field equals lambda 1 over 2 pi r epsilon naught. Okay, so if we compare this to what we did last week we calculated the electric field due to an infinite line of charge, did we not? I'm pretty sure we did. Yes, we did. And the end result that we got was this it? I'm pretty sure this was it. Yeah, we got, let's see. Here it is. 2k lambda over y, where y was the distance from the line of charge. So in this problem, we're going to be calling that r. Okay, so the r plays the role of the y. Let's see, 2k lambda over y. And what was k again for this? Oh, wait, k is just the Coulomb constant. Okay, so is this equivalent to 2k lambda over r? That's our question. Is this equivalent to 2k lambda over r? So if I write 2k lambda 1 over r, I can rewrite that as 2 lambda 1 over r times k, the Coulomb constant, is equal to 1 over 4 pi epsilon naught. So I can reduce the 2 and the 4, that leaves us a 2, and lambda over 2 pi epsilon naught times r. Yep, we got it. So yes, it agrees with the result that we got last time. Alright, so that leaves us with, I guess I'm just going to simplify it a little bit by moving the variable term out to the right. I'm going to gather all the constants together, lambda 1 over 2 pi epsilon naught, and then times the variable term is 1 over r. It's helpful to do it this way just because, you know, it's a little more organized knowing where your constants are and where your variable is. This makes it really easy to see what the shape of the graph is going to be at a glance. Because when it's just this big mess, you can hardly tell if it's going to be, you know, if it's going to resemble a linear graph or a quadratic graph, or in this case it's going to be just a reciprocal function graph. But yeah, moving your variables out when you can easily do so, makes it a little bit easier to figure out what type of function you're looking at, which can make the graphing part easier if your instructor follows up on questions like this by asking you to draw a graph, which is not entirely unheard of. It wasn't my favorite part of the course, but it is something that you need to be able to do. I'm not going to do a pre-calculus review here. You should know how to draw graphs, and if not, then go back to your pre-calculus textbook and practice. Anyway, I'm going to now continue with our next Gaussian surface, which is going to be a cylinder again of radius between A and B, radius r, whose value lies between A and B. So that's going to be roughly where it cuts through our cylindrical shell, and it just extends like that. This drawing is already getting really crowded. Okay, so for this one, whatever are we going to do? So I guess let me grab a new sheet of paper first. Let's see, Gauss's law, first and foremost, gives us, we already did the justification for writing the left-hand side as E times 2 pi r L. We already did that with this. Now we want to do the tricky part, figuring out the charge enclosed over epsilon naught. Okay, the charge enclosed. This time, what we have inside here is a section of our cylindrical shell, not the entire shell, but a section of it, and we have the entire infinite line of charge wrapped up in this Gaussian surface. So I'm going to say equals Q line plus Q cylinder, but only the portion of the cylinder that's actually enclosed, over epsilon naught. Okay, well, the Q line over epsilon naught part, we already took care of that. That gives us this, lambda 1 over 2 pi r epsilon naught. So that part is already taken care of. Yeah, divide 2 pi rl on both sides, and then we can separate these terms from each other. So E equals Q line over 2 pi r l epsilon naught plus Q cylinder enclosed portion over 2 pi r l epsilon naught. This part we already know. It just reduces to lambda 1 over 2 pi r epsilon naught. So I'm going to go ahead and copy that result over here. Lambda 1 over 2 pi r epsilon naught, and then plus, here's the part that is a bit more tricky. So how much of the cylinder's charge is enclosed? How much of the cylinder's charge is enclosed? We cannot use this lambda 2. We cannot use this lambda 2 because this lambda 2 is based on the assumption that if you go linearly through this cylinder, you're taking all the charge for every cross-section that you pass through along the length of the cylinder. And we're not taking the entire cross-section here. We're just taking a section that has a radius greater than a but less than b. So we don't have all the charge in there. We cannot use this lambda 2 here. Instead, we're just going to have to use the volume charge density that we were given to work with. That was one of our given constants, so we're just going to have to use it. So I'm going to call Q cylinder enclosed. I'm going to call it rho times V cylinder enclosed. not too different from the calculation that we did over here. We're still doing a larger cylinder minus a smaller one, except in this case the larger cylinder has a radius of r instead of b, where r is some variable between a and b. So equals rho times, I can factor out the pi. Let's see. Pi r squared L minus pi a squared L. Yeah, I can factor out the pi and the L for that matter. And I'll be left with r squared minus a squared. Okay, and now I can just put that in here, and that gives me, let's see, rho times pi times L times r squared minus a squared all over 2 pi RL epsilon naught. The L's cancel out, the pi's cancel out, and the rest is just variable terms. So let me go ahead and copy this over. We have lambda 1 over 2 pi epsilon naught times 1 over r plus rho over 2 epsilon naught times, the variable part is going to be r squared minus a squared over r. Let's see, did I copy that all correctly? To the epsilon naught. Moved the r over to there, that's good. Okay, we are good to go there. And finally, we can now do a cylindrical Gaussian surface surrounding the entire system. A Gaussian cylinder surrounding everything and enclosing everything. Again, any electric field that penetrates through this surface is going to penetrate radially, and therefore there's no flux coming out of the bases, so we don't even need to worry about calculating the areas of the bases of our Gaussian cylinder. You'd be multiplying it by the zero electric field going through it anyway. So only the side surface area counts, and let me switch colors here. What I would have is, well, let me write the Gauss's law expression first. So E times 2 pi RL equals charge enclosed over epsilon naught. So we're going to have the charge of the line plus the total charge of the cylinder this time, because the entire cylinder is enclosed, over epsilon naught. We can simplify this, divide by 2 pi RL, and split this into multiple fractions. So I would have Q line over 2 pi RL epsilon naught plus Q cylinder over 2 pi RL epsilon naught. This simplifies to what we had earlier, and this one actually follows this same pattern. Only difference is this time instead of using just the enclosed volume, well, the enclosed volume of the cylinder is all of its volume. So the radius of your outer cylinder is going to reach all the way to B and beyond. So in fact, we can, let's see, I want to do this up here. We can do E equals, for this part, that's just going to be lambda 1 over 2 pi r epsilon naught again, no surprise with that, plus, for Q cylinder, we can follow this same calculation except replace the r squared with a b squared. That gives me rho pi L b squared minus a squared is the total volume of charged cylinder contained within my Gaussian surface. I don't know why I curved that line. Divided by 2 pi RL epsilon naught. The pi's cancel out like before, the L's cancel out like before, and I get the expression lambda 1 over 2 pi r epsilon naught plus, I'm going to have rho b squared minus a squared over 2r epsilon naught. And I guess for each of these I'm just going to move the 1 over r outside so that my constants are grouped separately from my variables. But otherwise, it doesn't look too different from what we had for our second region of interest. So lambda 1 over 2 pi epsilon naught times 1 over r plus, whoops, that's not how you write a plus, plus rho over 2 epsilon naught times b squared minus a squared times 1 over r. And I definitely didn't leave enough room for this, but oh well. Even when I try to add extra space to plan ahead, it's whatever. This is why it might be better to actually just use a pencil instead of markers and pens. That way you can erase and make room for more if you didn't plan out enough space for your final answers. But it is what it is. Alright, where do I want to go from here? I have another problem involving spheres, and I've got one involving a sheet and a slab. And I see another one involving a cylinder that we could look at. I'm guessing that one is a conducting cylinder. Let's see. It's not really asking for much. Whatever, we'll work with it. We will work with it. Okay, let's take a look at this conducting cylinder situation. So we have, it says 2 coaxial cylindrical conductors are shown in perspective and cross-section above, so they've drawn something like this, and then on the inside is yet another cylinder. And both of these are conductors. And then they've got the cross-section view, which is just staring right down the thing. That is not a perfect circle, but I'm working with it. Oh god, it's terrible. We'll pretend that thing is a circle. Anyway, we've got radius of the inner cylinder is A, next radius is B, and next radius is C, as per tradition. You just label them A, B, C, D, and so on, from shortest to longest. They said that the inner cylinder has a total charge of Q on it, while the outer cylinder has a total charge of negative 2Q. And it's just asking for electric field, so that's what I will ask too. What is the electric field? What is the electric field in all regions of interest? Let's see. So regions of interest would include from 0 until A, assuming, of course, that we're using, again, Gaussian cylinders here that share an axis with our actual cylinders. So radius of our first Gaussian cylinder, our innermost Gaussian cylinder, will be somewhere between 0 and A. Then we're going to have something greater than A but less than B. So in here, then in here, then we're going to have it part way through the outer shell, and then we're going to have it all the way outside of the outer shell. So next one would be between B and C in terms of radius, and the last one will be just outside of C, wrapping around the whole entire system. Alright, so with conductors we have some really easy electric fields that we can put down right away. Last time we talked about how with conductors the electric field within the bulk of a conductor is always 0. So when your Gaussian cylinder goes through the inside of your inner conducting cylinder, since that's a conductor, if you're inside of it, your electric field there is 0. So that takes care of that one. And then when you're in this region of space, you're not physically inside either conductor, so there is going to be some non-zero electric field here. Well, I mean, you could still do the math and have it work out to be 0, but chances are that won't happen. And then our next region of interest with radii between B and C, that's where you're inside the body of another conductor. So for our third region of interest, we will have a 0 electric field. And that leaves whatever is going on in our second and fourth regions of interest. Should have made that a little bit longer from the beginning, but it's okay. All right, what can we do here? So, if I draw a Gaussian cylinder, I guess in this case I'm just drawing a cross-section of it on this cross-sectional view. If I draw a Gaussian cylinder that wraps around my entire inner cylinder plus some of the space around it, what can I expect my electric field to be? Well, by Gauss's law, we know that the flux, which is going to be E times, for cylindrical symmetry, 2 pi RL, equals the charge enclosed over epsilon naught, and they made this really easy because they told us how much total charge there is on this cylinder. It's big Q. We don't have to take a linear density and multiply it by the length because we don't have to. Divide by 2 pi RL and we're done. E for our second region of interest equals big Q over 2 pi RL epsilon naught. Now, some of you might be saying, well, wait a minute, aren't we just going to get 0 out of here because L is infinity? Well, for this problem, they actually did not give us a cylinder of infinite length. They actually have a finite length this time, so we are fine. Now, technically, because the length is finite, there's going to be some electric flux coming through the bases of our Gaussian cylinder, but if this, what is this supposed to be? I guess it's supposed to be a coaxial cable. If this coaxial cable is long enough, then that little bit of flux is going to be negligible. So we are actually fine with just this. I am going to move the 1 over r term outside though, just because, as I've been doing with all these other problems, I like to keep the variable term separated if I can. And then times 1 over r. Did I copy all the constants right? Yes, I did. Okay. And then for our fourth region of interest, where your Gaussian cylinder wraps around the whole entire system, it's going to be just as easy. So we would have, once again, E times 2 pi RL equals, this time the charge enclosed is the total charge of the inner cylinder plus the total charge of the outer cylinder, which is just going to be Q1 plus negative 2Q. Wait, did I call this Q1? Big Q plus negative 2 big Q. All over epsilon naught, divide by 2 pi RL, and we get Q minus 2Q is minus Q, and then the rest is pretty much the same. Alright, so nothing too surprising there, but here's something they didn't ask, which I will ask. How much charge is on the inner surface versus the outer surface of your cylindrical shell? We know for the solid cylinder in the middle, all the charge is distributed on the outer surface because there is no inner surface. But what about the cylindrical shell? How does the charge distribute there? Well, we know because the electric field in our third region of interest has to be 0, we know that if I were to draw a cylinder here, if I were to draw a Gaussian cylinder here that encloses the inner surface of the outer cylinder plus the entirety of the inner cylinder, I know that the charge enclosed must be 0. And since I enclose a charge of positive Q from this inner cylinder, the inner surface of the outer cylinder must carry a charge of negative Q. So that means if I redraw the outer cylindrical shell, if I were to redraw it, that means that I have a charge of, and I guess I'll redraw the inner cylinder as well. I've got a charge of Q on the surface of the inner cylinder, and then I've got a charge of negative Q on the inner surface of the outer cylinder. And since the total charge on the outer cylinder is negative 2Q, since I already have negative Q on here, that means that whatever charge is on the outer surface combined with this negative Q adds up to negative 2Q, so I also have another negative Q on the outer surface of the outer cylinder, giving you your grand total of negative 2Q. An exercise that is often neglected. I mean, even the authors of this book didn't even bother to ask you, unless I didn't read the question carefully. No, they don't ask. Which is a shame, but maybe that was their attempt to have mercy on the student reading this textbook. Okay, let's move on to a different type of symmetry, and then if we have time left over, maybe we can do an example or two involving electric potential, although that's seeming less and less likely as we go. I mean, with about 40-ish minutes left on the clock, we might have the chance to do one. We'll see. Okay, so next scenario that I have is an infinite charged sheet and infinite conducting slab. I guess before I do that, let's talk about how we work with planar symmetries. So if I have a plane, if I just have a flat infinite sheet of charge with a surface charge density sigma, and let's assume this sheet is positively charged for the sake of simplicity. We can deal with negative charge in a minute. But let's work with positive charge first. And I want to figure out the electric field due to this infinite sheet of charge. One way you could do this is with calculus. Good luck with that. I mean, it's not impossible, but it's very inconvenient. Instead, we can just take advantage of Gauss's law. So what I'll do is I'll draw a Gaussian surface. In this case, I'm just going to draw a Gaussian... you could go with a cylinder, but honestly, any prism will do as well. I'm just going to go with a rectangular prism here. And I'm going to actually have it go underneath here as well. If I draw this right, then something like that. And I guess I should have used dotted lines for that too. Actually, wait, hold on. No, that does not need to be dotted. That does. That does not, and that does not. Okay, that looks about right to me. So if I use a rectangular prism as my Gaussian surface, let's see, what kind of electric field would I get out of this? First off, if you have an infinite sheet of charge, then similar to what we did last week with the infinite line of charge, let's see, where is it? Similar to what we did last week with the infinite line of charge, for every point on the surface of your infinite sheet that produces an electric field at some point outside of the sheet, there's always going to be another point on the opposite side of the sheet that cancels any components parallel to the sheet, leaving you only with the electric field components that point directly away from the sheet, perpendicularly away from the sheet. If you assume your charges to be positive, if the charges are negative, then it would just point straight down, but that's also perpendicular. So the point is your non-perpendicular vector components are going to cancel out. So the only electric fields that you're going to have in the end, since this sheet is infinite, the only electric fields you're going to have are electric fields that point perpendicular to the sheet. So either straight up on this side of the sheet, or if you're on the bottom side of the sheet, you're going to have electric fields that point straight down. And since you don't have any electric fields pointing parallel to the sheet like this, since you don't have any of those, I'm just going to cross them out. Since you don't have those, there's going to be zero flux through the side surface of your prism. And since you have zero flux through the side surface of your prism, you don't need to waste time calculating the side surface area. If you're going to multiply it by zero electric field anyway, if you're calculating flux as the integral of E dot dA, there's no point in calculating the dA part when the E part is 0. So yeah, we don't need to worry about the side surface area. We only need to worry about the top surface and the bottom surface. So we'll just have an electric field over here times whatever that area is, plus an equal amount of electric field down there times that same area. So I'm going to have 2 times whatever that electric field is times the area. I'm just going to call it A of the base. I guess I'll call it A base. And you cannot read that. I'll write it here a little bit more clearly. 2E times A base is the total flux, equals charge enclosed over epsilon naught. The charge enclosed is equal to the surface charge density times the surface area enclosed. And what's the surface area enclosed? Well, if I take a look at the section of this infinite sheet of charge that is actually enclosed by my rectangular prism, and I guess I drew it a bit slanted because I didn't plan carefully when I drew this thing. Hold on, let me try again. That looks a little bit better, but still doesn't look quite squarish. Anyway, this area enclosed is the same area as the two bases. So in fact, it's sigma times A base is your A enclosed over epsilon naught. The A's cancel out. So that leaves me with, let's see, 2E equals sigma over epsilon naught. Let me write it up here. So 2E and then A base equals sigma A base over epsilon naught. The area cancels out, divide by 2, and the electric field, at least its magnitude, is equal to, if you divide by 2, sigma over 2 epsilon naught, or if you prefer, you can also pull the 2 out and write it as a 1/2 instead. Okay, so the good news is after getting this result, you don't have to do Gauss's law for sheet symmetries ever again. You can just remember this result and use it as many times as you need to whenever you're dealing with this type of symmetry. So this type of symmetry applies to not only infinite sheets, but also slabs, which can be thought of as a pair of sheets with a region of zero electric field between them if the slab is a conducting slab, which it usually is. Let's go ahead and look at an example and it'll be more clear. So we have an infinite charged sheet and an infinite conducting slab. Let's go ahead and start that on a new sheet of paper. So they've drawn the sheet sideways, which, well, sideways doesn't really mean anything here. They've drawn it from a perspective that's parallel to the sheet. So like you're looking down at it like this, which is I mean, the way they've drawn it, I guess I'll just show you the drawing. This is what they drew, and I'll try and imitate that, but I don't know how well I'm going to be able to draw what they have. We'll see. So I'm going to do, let me think, if the slab is going to be bigger than, I think I want to draw the slab first. Okay, something like that. And then for the sheet, I'm just going to, if I draw it further, then I don't have to worry about it overlapping with that. Okay, yeah. That wasn't as bad as I expected it to be. Draw that a little bit straighter. Yeah, there we go. All right, let's see here. So they just gave us sigma 1 to represent the surface charge density of the sheet, and they gave us the total charge per unit area for the conducting slab is sigma 2. We're going to have to actually split that between the two sides of the slab. If that doesn't make sense to you yet, we'll clarify that soon. Anything else that they included here? That might make for an interesting question, or should I just go ahead and work with what I have and ask my own? Let's see. Okay, so they're just asking the same questions that I was going to ask anyway. So, one of their big questions, aside from asking for what the electric fields are in different regions, they're also asking for this, which they called sigma A, and this, which they called sigma B. What are the surface charge densities on the left-hand side of the slab and on the right-hand surface of the slab? That question we can answer later, but first we need to look at our electric fields. So for our electric fields, what are our regions of interest? Our regions of interest are here. So I guess what I want to do is also just draw an x-axis. There's an x-axis, and then this is at x equals 0. Where do I want to write this? I guess I'll write it up here. X equals 0. Right there. This is x equals a. This is x equals b. And then that's greater than b. So our regions of interest are going to be where x is less than 0, and then between 0 and a, where x falls between 0 and a, and then when x falls between a and b, and finally where x is greater than b. So that's 4 regions of interest: here, 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 and out here. Okay, one of these is going to be really, really easy because for a conducting slab anywhere inside the bulk of that conducting slab, the electric field must be 0. The electric field in here has to be 0. Done. All right, and then for the rest of this, we've got some work to do. So the main difficulty with planar symmetries is just keeping track of your signs and directions. That's usually what trips students up when it comes to these types of problems. For now, I'm going to treat these sigmas as if they're positive. So I'm going to say that in this region, electric field due to the sheet is going to point to the left. If you assume it's positively charged, then it's going to create an electric field away from the sheet rather than towards it. So I'm going to call that E sheet. Actually, I will call it E1 since the surface charge density of the sheet is called sigma 1. Yeah, I'm going to call that E1. And then for the slab, it's got a total surface charge density of sigma 2, so it's going to create an electric field. If we assume sigma 2 to be positive, it's going to create an electric field to the left as well of magnitude E2. And we can use the conclusion that we got earlier, E equals sigma over 2 epsilon naught, to figure out what the magnitude of that electric field is. So total electric field in this region, we've got E1 is sigma 1 over 2 epsilon naught. E2 is sigma 2 over 2 epsilon naught. And so your total electric field here is E1 plus E2, so E total for just this region when x is less than 0 is going to be sigma 1 plus sigma 2 over 2 epsilon naught. Okay, easy enough. So I'll go ahead and copy that over here. Sigma 1 plus sigma 2 over 2 epsilon naught. And I guess since it's to the left, I could tack on a negative sign here, but I'm just going to add the word left for now. Actually, you know what? Yeah, I'm going to tack on a negative sign because I'm just assuming the signs of sigma 1 and sigma 2, and if it's opposite to what I assume them to be, then I would want to have a negative sign cancel them out. Okay, let me cross out this. Yeah, forget what I said over there. Okay. Next up is the region between x equals 0 and x equals a. So over here, we have the electric field due to the sheet points to the right. So that's going to be E1. The electric field due to the slab points to the left, because we're still left of the slab, so that's going to be E2. And so if I take right to be positive, then essentially what I have here is E1 minus E2, and E1 minus E2 is just going to be sigma 1 minus sigma 2 over 2 epsilon naught. And yeah, just copy that over, and we're good to go. So I'm just using right as positive for this problem, it seems. I'm going to try and stick with that. And then finally, we already did our third region of interest. That's going to be 0 just because of the nature of conductors. That leaves us with our third region of interest over here. From the sheet, we're going to get an electric field of E1 pointing to the right, since we're to the right of the sheet. And since we are to the right of the slab, we're also going to get an electric field E2 pointing to the right as well. Again, this is assuming that these that the charges on here are positive. If they come out to be negative, then that's fine. If you plug in negative values for the sigmas, then you should be able to get the correct overall sign, at least using the convention that I'm using. So we can just write, well, it's going to be E1 plus E2, but this time the net electric field is to the right, So I don't need the negative sign that I included over here. So I just get sigma 1 plus sigma 2 over 2 epsilon naught without the negative sign in front. And there we go. So that takes care of defining the electric field in our different regions of interest. Now our next question is, what is sigma A and what is sigma B? What is sigma A and what is sigma B? So essentially, what you're doing here is think of it as replacing this infinite slab with just two sheets whose total surface charge density is sigma 2. So whatever sigma A is and whatever sigma B is, sigma A plus sigma B at least, hold on. Let me think about what I'm about to say, because this is a common pitfall. Sigma A plus sigma B has to equal sigma 2. Okay, good. Sigma A plus sigma B has to add up to sigma 2. Okay, the electric fields that they generate, if I redraw this whole situation, but instead of drawing a sheet and a slab, I draw 3 sheets. Okay, something like that. So sigma 1, sigma 2, and sigma B. Okay, the only region of interest I'm going to focus on this time is just right here between... Uh-oh, did I write a 2 there? That's supposed to be an A. The only region of interest I want to focus on this time is the region between these two sheets, which is supposed to be the bulk of the slab in the original drawing. Over here, you're basically looking at the sum of 3 electric fields, one due to this sheet, one due to this sheet, and one due to this sheet, that must be 0. So from this sheet, I'm going to have E1 pointing to the right. I'm assuming positive sigma values here, which might not even be true, but treating them as if they're positive for a minute, I'm going to have E1 points to the right, and since we're to the right of sheet A, EA would also be to the right. And since I'm to the left of sigma B, assuming that sigma B is positive, EB would be to the left. EB would be to the left. And that all has to add up to 0. So E1 plus EA plus EB, E1 plus EA plus EB, well, actually, wait, no, minus EB has to equal 0. E1 is sigma 1 over 2 epsilon naught. EA is simply going to be sigma A over 2 epsilon naught. And EB is going to have a magnitude of sigma B over 2 epsilon naught. So I'm going to have sigma 1 plus sigma A minus sigma B each over 2 epsilon naught. You can cancel that out. Has to equal 0. I could write over 2 epsilon naught for each of them, but it's if I multiply the whole equation by 2 epsilon naught, then the right-hand side would still be 0, and the left-hand side just simplifies to not being fractions anymore, which is preferable. But now you've got 2 equations in 2 unknowns. Remember, sigma 1 is already known, as is sigma 2. So with these 2 equations, you should be able to solve for sigma A and sigma B. Let's see what they would be. If I simply add the top equation to the bottom equation, then I will have sigma 1 plus 2 sigma A plus 2 sigma A, and then sigma B and minus sigma B cancel out, and then sigma 2 plus 0, so equals sigma 2. Subtract sigma 1 and divide by 2, and I get sigma A is equal to sigma 2 minus sigma 1 all over 2. From this, I can go back to either equation. I'm just going to go to the first one, and I'm going to substitute. If sigma A is sigma 2 minus sigma 1 over 2, I'm going to write times 1/2, and then plus sigma B equals sigma 2. Then if I distribute the 1/2, I'll have a half sigma 2 there, and minus a half sigma 1. The half sigma 2, if I subtract it from the sigma 2 over there, then I'm left with a half. So I'd have minus 1/2 sigma 1 still on the left-hand side, plus sigma B equals sigma 2 minus half of sigma 2 is 1/2 sigma 2. So add 1/2 sigma 1 over to the right-hand side, and sigma B is going to be the sum of sigma 1 and sigma 2 over 2. Right? I'm going to have, oh boy, running out of space here, but I think I can squeeze it in. I'm going to have sigma B left behind equals half sigma 2 plus the half sigma 1 after you add it over equals sigma 1 plus sigma 2 all over 2. Yeah, I probably shouldn't have tried to squeeze it all in there, but I guess I'll rewrite both expressions over here for added clarity. So sigma A equals sigma 2 minus sigma 1 all over 2, while sigma B equals sigma 1 plus sigma 2 all over 2. Let me see. If I add them together, then minus sigma 1 and plus sigma 1 cancels out, and I get 2 sigma 2 over 2 equals sigma 2. So yes, they do still add up to sigma 2. Our math checks out. Okay, so this was calculated based on the assumption that sigma 1 and sigma 2 were positive values, and I guess we're also treating sigma A and sigma B as being positive as well. But if you get actual numbers to plug in here, then this math will still work. Whatever we assume to be positive, if you do the math and you come up with a negative instead, that's okay. If you substitute it as a negative in here, then you will get the correct directions. And yeah, I think that's all I need to say here. If I knew the signs in advance, I would, instead of using negative for left and positive for right, I would just decide whether to add or subtract based on which direction had electric fields of greater magnitude. Which probably doesn't make sense if I don't give an example with actual numbers, but I guess I've shown one of two conventions you can follow, and if it works for you, then I think that's good enough. With 10 minutes left on the clock, you know what? Let's try and do it again, but this time with some numbers assigned. Let me see. Do I want to use the numbers that they have? So they assigned a value of sigma 1 equals negative 4.4 microcoulombs per square meter, and sigma 2 equals 90 microcoulombs per square meter. So they gave us sigma 1 equals, I'm not going to worry about the fact that they're microcoulombs, I'm just going to say negative 4.4 units, and sigma 2 was positive 90 units. Okay, so if I substitute in those values, I'm going to get, this was actually to the left and not to the right, since E1 is actually going to be negative due to sigma 1 being negative. So how does that change things? So I would have done, if I knew the values ahead of time, or well, if I cared to use them ahead of time, then I would have drawn E1 pointing to the left on this side. Or wait, no. What am I saying? If I know sigma 1 to be negative ahead of time, then what I would have done is I would have drawn E1 pointing to the right, like this, on that side, and I would have drawn E1 pointing to the left on the right side of this sheet. And then from there, I would have done E2 minus E1. E2 to the left minus E1 to the right equals, let's see, 90 minus 4.4. So essentially, I would abandon the negative sign from here and just calculate the magnitude of E1 and then decide whether to add or subtract based on the directions instead. So that is something that you can do if you know the signs of your charge densities in advance. If you don't know them in advance, then just do what I did for this whole problem. Treat everything as if it's positively charged and let the math determine what signs you end up with. So if we did just stick with, if I did treat E1 as pointing to the left here instead of to the right, then after subbing in a negative value here, I would have had, let's see, negative sigma 1, so negative 4.4 would be positive 4.4, which makes sense because its actual direction is to the right, and then minus positive 90, which also makes sense because E2 is to the left. So you would have ended up with an overall negative electric field whose magnitude is the difference in magnitude between these two which is correct because in actuality these electric fields would be opposite to each other once you substitute a negative value in for sigma 1. I feel like there was something else I wanted to say, something else I wanted to comment on this, but I'm drawing a blank right now. My point is, if you know your charge densities in advance, then you can write your electric fields as just magnitudes without having to worry about their signs, and then determine their signs from your drawings. Otherwise, if you don't know them in advance, again, do what I did for this whole problem and treat everything as if it's positive and use negative for left and positive for right. And be very careful about assigning negatives to the magnitudes of your electric fields in that case, because the common pitfall that students tend to fall for with these is they forget that the electric field due to any individual sheet is going to have opposite directions on opposite sides of the sheet. And that's where you can really create a mess for yourself if you don't choose one of these two conventions right from the start of the problem and stick to it. I guess that's what I've been trying to say this whole time, but just couldn't quite get the words out until now. But yeah, with 3 minutes left on the clock, I guess we're not going to have time to look at voltage. So maybe I will save that for next week, unless something else comes up that I would rather cover instead. But I don't know. I mean, my mechanics students, most of them are finishing up, so I don't think they need any more mechanics stuff for a while. I'm probably still going to stick with electricity and magnetism next week, but we will see. I'll come up with whatever I come up with for next week. But I guess that'll be it for today. Hopefully this has been helpful. If there's anything specific as a topic that you would like to request for next time, then show up. Show up and ask questions in the chat, or if you don't have time to show up the day of, leave questions in the suggestion box for what you would like me to cover. And if it's something that I can cover well enough and I've done any review that I might need to do, then I'll cover it. But that'll be it for tonight. Take care, and I'll see you next week.